to write down 3 things to begin these. 3 things. You're going to draw a sketch of what's going on so you can understand what's going on. Like, what's the system in play? But the 2 things you need to remember are, what do you know? You're literally going to write down the word know, and you're going to write down the word want. Meaning, what do you know? What is the question giving you? And you're going to write down what you want. So it's going to be a sketch, know, and want. You do not, when you try to solve an algebraic equation, you solve it all at once. No, there's pieces you figure out first. If you have a clear picture that is labeled properly, and you clearly write down what all of the things you know and all of the things you want in proper notation, these questions tend to be really straightforward. The investment of time is honestly at the beginning, setting up the equations. If you just try to set up the equation straight out, it's super easy to make simple mistakes. So I'm going to show you what I mean. So it says, suppose you have a rocket ship 3,000 feet away. So you're standing right here and a rocket ship is 3,000 feet away, and you have a camera taping the launch. You're assuming also, it doesn't say that the camera's off the ground, so the camera's on the ground, okay? After launch, when the rocket is 400 feet in the air, we know that it's 4,000 feet in the air, we know that it's rising at a rate of 800 feet per second. How fast is the camera to rocket distance changing at that instant, okay? What type of shape are we going to end up using in this? What type of shape do you think is being formed here? We're assuming the rocket's going straight up. So let's draw this. So don't, everybody put your styluses down, watch this first, okay? It's important. So what's going on here? You have the person, and then how far away is the rocket? Is that distance changing? No, that distance doesn't change. And is the rocket going straight up? Is that something you can assume? Yes. So the rocket is going up, right? And how fast, does it say how fast it's moving?
Yeah,
880 what? Feet per second, right? And then it says, are there any other things we can write down here? So this is just a picture of what we want.
the rocket is 4,000 feet.
So it says after the launch, when the rocket is 4,000 feet in the air. So we need to start labeling things here. So label them clearly. Don't pick arbitrary letters. So if the rocket's going up, what letter do you think we want to use? Height. So let's use H. Okay. So if we're going to label this is important, everybody. We're going to call this dH dt. What is that? That is the change in height with respect to what? Time. You okay with that? Which distance are we trying to find here? If I haven't drawn in which distance are we trying to find? Let's call this point A, B, and C. A to C, right? And we can pick something here. Let's label that distance. Let's call that D. Is that okay? So let's call that distance. Well, no, let's call it something other than D because I just don't want to use that. Let's call it L. Is that okay? So what do we want? So this is what we know. We know this. What do we want?
L. A to C.
We want A to C, but we don't want the distance. What do we want?
The rate.
The rate. So the change of what? The change of
A to C in terms
Oh,
of
the change of
L.
range.
The change of L, right? The distance from the person to the camera to the rocket, right? So what do we want? We want dL dt when what?
It's 4,000 feet.
When what is 4,000 feet? When h equals 4,000. Exactly. Do you see that, everybody?
Yeah.
You have a picture of what's going on. You've written down what you know, and you've written down what you want. You start there. Do not write the equation yet. After you do these 3 things, most things fall through really nicely. So what we assume that triangle is a what?
Right triangle.
A right triangle. Yes. We're assuming the rocket goes straight up. In actuality, do they always go straight up? Not so much, right? Okay. You now need to link. So you write down, you have a picture, you know what you want, and now you want to write down an equation that links. What do you think you have to link together? What do you think you have to link together? Well, what you know and what you want. What equation do we know that links everything together on a triangle? The Pythagorean Theorem. Base squared plus height squared equals hypotenuse squared. What's the base? What's the base? Does that change? No, so it's 3,000 squared plus what squared? Careful here. Careful. What's changing? The height is changing, right? So it's going to be plus h squared equals what? L squared. Do you agree that that's true? If you have a given height and you wanted to find L, that is what you would write down. Are you okay with that?
Well, wouldn't you put 4,000?
We will eventually, but that's at a specific instant. This is that we haven't differentiated yet. So now that you've written the equation, what do you think you have to do next? I just told you. What do you have to differentiate? With respect to what? Nope.
The rate that the run is going on.
What you differentiate with respect to is the denominator of all those differentials right there. Time. You differentiate with respect to time. So you see all these, right? The dH dt and the dL dt. So what are you differentiating with respect to? T. Remember we did that a little bit with implicit? We're doing implicit now. So if I differentiate this, what's the derivative of 3,000 squared with respect to time? Come on.
I don't like.
What's the derivative of a constant? 0. Thank you. 0 plus, what about h squared? What does that become? 2h times what? 2h times dH dt. Remember the chain rule? Remember what implicit does here? It kicks out. Remember how I'm not going to substitute h of t in. I'm just going to do it. It is the chain rule. We're doing it with respect to t. What does the right-hand side become?
2L times DL dt.
Yes. And now what have we linked together, everybody?
Should we write if we wanted to L prime and H prime?
Yes, absolutely. I would prefer you do it in this case because the t is really important to realize that it's there, okay? But have we linked them together now?
Yes.
So what can we now substitute in? What do we want? What do we want? We want this, right? We want dL dt?
Substitute 4,000.
Oh, so where can we put in the 4,000? H, that goes right where?
There.
We can drop those 2's, right? Because we can divide both sides. So what do you get? 4,000 times, oh, what is dH dt? 880 equals L times what?
L prime.
dL dt. L prime, yes, you could say L prime, but dL dt.
DH dt 880
Because we told it to. Look, it told us.
at 4,000.
At 4,000 feet, the rate of change of the height is 880.
Okay.
We know, right?
Yeah.
Okay, so here's the thing. We substituted one thing. We substituted another. We want this, right?
Yeah.
So what do we need to substitute for? L. We need to know what L is. We need to know what L is when this is 3,000, this is 4,000. What is L? What is L?
So we gotta do the 3.
What is L when base equals 3,000? Don't use a calculator. And height equals 4,000. You don't need a calculator for this. This one is set up really nicely. If the base is 3,000 and the height is 4,000, what's the height? Sorry, the hypotenuse. 3, 4, 5, right? It's a 3, 4, 5 triangle. This one was set up really nicely for you. What's 3 squared plus 4 squared? 5 squared. What's 3,000 squared plus 4,000 squared? 5,000 squared. So what is L? 5,000. When the base is 3,000 and the height is? Exactly. So we can now take this and where do we plug it in? So we have 4,000 times 880 is equal to what? 5,000 times dL dt. Can we now isolate it? We absolutely can. What can you drop on both sides? We don't need the zeros, right? So what do you end up with? 4 over 5, 880 equals dL dt. Could you do that in your head with 8? So what is that? That is 4 times 88 times 2 equals dL dt. Can someone just tell me what that is? That's 160, 176 times 4. I'm just trying to do this all in my head, and I'm not super good at it. 176 times 4. What is it, Chris? What is it? What is it?
704, like that's 0.8 times 880.
Yeah, so dL dt is what?
70 equals 704.
704?
That's what's on the other side, yeah.
704. So dL dt, the rate of change is 704. What's the rate? What's the unit on this? It's a rate of change of feet per second. Yeah. So there it is right there. So again, let me just recap this. What do you do first? What do you do first? Picture, know, and want. Until you do that, do not write an equation. One of the biggest ways to make it harder for yourself is to try to construct the equation first. This is just another word problem. Do you create the equation first? No. You have to isolate what you know and what you want and what's actually happening. Then you write the equation, and you have to think about what are you trying to link together. In this case, it was dH dt and dL dt. And the linking equation, you're going to love triangles. Triangles offer you, right triangles offer you really nice equations. Now, just as a side note, could we do this question where the rocket was going not straight up? What would change? Could we use the Pythagorean theorem? No. Do you know what theorem we'd have to use instead? Not theorem, but what trig equation would we have to use instead? Come on, you know, like if you have a triangle, if I gave you this right here, if I said this was 6, 7, and this was like 130 degrees, what equation do you use to find this?
Oh, is that like tangent or like?
No tangent. No. Law of cosines. You'd use law of cosines on this one, right? You'd have to use law of cosines. But so right, are you really gonna really like right triangles?
Yeah.
Absolutely. Now here's the thing. All happening to this circle.
The radius is increasing by 2 feet per second.
So there's a circle here, right? So, oh, it's frozen, sorry. It's getting bigger, do you agree? So if we need to label that, what did I just draw in there? What is that? That's a radius, do you agree?
Yeah.
It's getting bigger, yay. So what were those two words I want you to write down? What do you know and what do you want? What do you know? What do you know?
It's growing.
What is growing?
Growing
at a rate of
2 feet per second.
So give me the notation for that. dr dt is equal to what? 2 feet per second. Yes, that's what you just. You know that the radius is growing at 2 feet per second. Correct. So that right there, where does that correlate to? That is increases at a constant rate of 2 feet per second. Okay, what is the area? How fast is the area of the spill? So you want the rate of change. You want the rate of change of the what? You want the rate of change of the what? The area, right? So how do you write rate of change of area? dA dt. You want dA dt. You know dr dt and you want dA dt. Is there an equation that links together area and radius? Yeah, there is. What is the equation that links together area and radius? Yeah, you do.
I mean, I do know that.
What is it? It's a circle. What's the area of a circle?
Pi r squared.
Pi r squared. Thank you. Yes.
Yeah.
Do you agree that the area of a circle is pi r squared?
Yeah.
Nice. So what was the next step after? So, oh, look, we have an equation that links together area and radius. Can you take the derivative now?
Yes.
What are you taking the derivative with respect to? Time. So what's the left side going to become? dA dt, yes, equals pi times what?
60 squared.
No, don't plug anything in. Do not plug anything in. 2 times r times dr dt. Oh wait, do we know dA dt? No, we want dA dt, right? What do we know? We know dr dt. Where can that go? Right there. So we have dA dt is equal to 2 pi r times what? 2. There's still something we need to get rid of, though. What's the thing we need to get rid of? The 2. It brought down to the front, right? It marches down to the front. Goes right there. So what's the last thing we need to get rid of? The r. So we want dA dt when what? When r is what?
60.
Oh, when r is 60. Does it actually give us the r?
Yeah.
So where do we plug that in? For r. And what do we end up with? dA dt is equal to 2 pi times what?
60
Times 2. So what is that?
2 pi.
240 pi. What are the units on this? This is, when you do these clean, they're going to go like that. Can someone tell me what the units are? This is a rate of change of area, right? Based on what they told you here, what are the units on this?
Yeah. 2 feet per second.
For area. Area is measured in what? In area, not volume. Area. Feet. Area, not volume.
Oh, yeah, sorry. Feet squared.
Feet squared per second. I know in physics you're supposed to keep your units like all the way through. For me, you just need to write the units at the end. That's fine, but you have to put the units on this. It's also really important because it's a great spot check to see if you're in the right universe. Like, does that vaguely make sense? Sure, it's going to be a big circle, right? What's interesting to think about this, if the radius increases at a constant rate, this number is going to keep on getting bigger and bigger. Why? Well, think about this. If you have a really small circle and you increase its radius by 2 inches, you might like double the area, right? So it might go from like 8 to 16, something like that, right? But let's say you had a circle the size of planet Earth. I'm serious. Let's say you had a circle the size of planet Earth. And let's say you change the radius of Earth by 2 inches. How much area did you just add? Billions of square miles.
A lot.
The ratio is smaller, but how much did you add? Literally billions. So like if you had a golf ball made out of clay, okay, and you added 2 inches of radius to it, you would turn this. You'd add maybe like, I don't know, like this much clay to it, right? But let's say you had the Earth, right, and you added 2 inches all the way around planet Earth. How much clay is that?
A lot.
Trillions and billions of metric tons, right? The point is, this number will get bigger and bigger. You're like, oh, it's getting smaller. Well, the ratio is getting smaller, right? Like that trillion billion miles of clay is much a smaller ratio to the whole Earth, but it's way much more.
It's like sea level rising. It's like
Yes.
nothing, but that's like tons of water.
Tons of water, exactly. So like, if the sea level goes up by a centimeter, like how many icebergs have to melt? Like a lot of stuff, right? So that, but you look at the inverse of that. If the sea level goes up, how much water has been now added to the system? A lot, right? Like a ton. As a side note, if you want to see a really cool data infographic,